Mass spectrometry. Okay, welcome to today's chemistry class on mass spectrometer. So this is a diagram of a mass spectrometer. Now, when we talk about mass spectrometer, what is mass spectrometer? Okay, so mass spectrometry is a technique. So it's spectrometry. So mass spectrometry is a characterization technique used to determine the relative atomic mass and the relative abundance of isotopes, and also for chemical analysis and the study of ion reactions. So we use the mass spectrometer, which is the instrument. So then we use the mass spectrometer for mass spectrometry. That is the technique for determining relative atomic masses, the relative abundances of isotopes for chemical analysis and for ion reaction. So what happens is that the mass spectrometer separates positive gaseous ions according to their mass per charge unit. So now, if you have a mass spectrometer, like for instance, if you have a steel ball and want to determine the chemical composition of a steel ball, and we know that a steel ball contains iron and carbon. They make up what we refer to as a steel, the alloy. So you want to know the amount of iron present in the steel ball and want to know the amount of carbon present in the steel ball, we can use the mass spectrometer. That is the technique as mass spectrometry to determine the chemical analysis of the steel ball. Again, too, we want to determine the relative atomic masses of a substance or the relative abundance of isotopes of an atom. You can also use the mass spectrometry. What is an isotope? You know that we have allotropes and we have isotopes. Now, what happens is that when you say an allotrope of an allotrope of an atom, what it means is that they have the same chemical element. They have the same chemical element, but their structure is different. So when you say there's an allotrope, they have the same chemical element, but their structure is different. When you say an isotopes, they also have the same chemical element, but they differ from their proton numbers. That is, they differ from their mass numbers, but they have the same chemical element. So we can say, for instance, for copper, you have 63 copper and you have 65 copper. So these two of them, they are isotopes. But copper itself is, I think, 29. Yes, copper itself is 29. The 29th element, scandium, titanium, vanadium, manganese iron, cobalt, nickel, copper, zinc. So zinc is 30, copper is 29. Like when you look at it, you realize that their proton number is the same. But what happens is that, their electron is the same, their proton is the same, but what happens is that there is difference in their mass numbers. And the difference in their mass numbers might have result from the difference in their neutron numbers. Okay, that is the isotope. But for isotopes, you can have let's say the carbon allotrope. You can have many allotropes, the oxygen allotrope, that's the oxygen gas, and the ozone. So what you realize is that these are allotropes of oxygen. So the oxygen is O2, the ozone is O3. They are made of the same chemical elements, but they have different structures. Okay. And we can use the mass spectrometer to determine the relative abundance of isotopes. Okay. Now this is the mass spectrometer. How does this work? So let me put it here. How it works. So the mass spectrometer, how it works. So I'm going to recite them out. So if you are with your book, you can write the process down. But this is the figure that will help us understand how the mass spectrometer works. Now what happens is that in the mass spectrometer, we place in a substance. So the substance here which can be bombarded, we can say maybe radium. So we have a substance here. You can say radium, a radioactive substance. Okay. Now this sample, the sample that is present here in the vaporization chamber, it's vaporized into gaseous sample. So the sample that is present here is vaporized into a gaseous sample. So here you have what? A gaseous what? sample. Now the gaseous sample will now enter into a chamber. That chamber is known as the ionization chamber. So the gaseous sample here is now ionized in the ionization chamber by bombarding it with high energy electrons. So in the ionization chamber, you bombard the gaseous sample with high energy electrons to ionize it. Now these high energy electrons, you get it from the hot filament over here. And what happens is that the electric plate will attract the sample. The ionized sample will be attracted because you know that it's an electric plate. I getting it? And yet it's ionized, so it's now in terms of an ion. I getting it? So it will be attracted by the electric plate, and when it's attracted by the electric plate, it is accelerated onto a magnetic field. So it is accelerated within what? A magnetic field. Now what happens is that the magnetic field will deflect the ionized sample onto a detector. The magnetic field will deflect the ionized sample onto a deflector. So we start from here. The sample here is what? Is vaporized into a gaseous state. The gaseous sample is ionized by bombarding with high energy electrons. The ionized sample here is attracted by the electric plate, and the electric plate will accelerate the ionized sample onto the magnetic field. And the magnetic field will deflect the sample onto a detector to be seen on the detector. I get it. So sometimes to be seen on the detector, that process is what is referred to as scintillation. Scintillation. So the process where we see flashes of light on a zinc fluorescent tube. On a zinc fluorescent tube, the alpha structure experiment, the zinc fluorescent tube where you see the flashes of light, that process is known as what? Scintillation. Okay. So now, when it comes on the detector, what happens is that according to their mass to chain ratio, the heavy ions will be deflected towards the detector, and the highlighter one will be deflected away, and you have the focused ions. So after that, the sample is now given onto an amplifier for amplification. The sample is given onto an amplifier for amplification, and the sample onto the amplifier for amplification is now given onto what? The recorder. Okay, so from the detector here, what happens is that it is given onto the amplifier. I get it. So the amplifier will make the amplification, and it's also given onto the recorder. Now the recorder draws the mass spectrum of the ions. So the function of the recorder is that it draws the mass spectrum. The recorder draws the mass spectrum of the ions. The recorder draws the mass spectrum of the ions. Okay. Now, how do we interpret the mass spectrum? Interpreting the mass spectrum. Okay. Interpreting the mass spectrum. Okay. So now the mass spectrum is a graph of percentage abundance. The mass spectrum okay, so the mass spectrum is of the graph of percentage abundance against the relative atomic masses of the ions. So the recorder will draw a mass spectrum, and the mass spectrum is this graph of percentage abundance on the y-axis against the relative atomic masses of the ions. So now you realize that there will be some values here, and you get these corresponding values as percentage on the mass spectrum. So these are the mass spectrum, or the recorder will give you the mass spectrum. Now, out of the number of peaks, take note, out of the number of peaks you get on the mass spectrum, it will determine the number of what? Isotopes of that particular sample. It will determine the number of isotopes of that particular sample. So for instance, if you have copper as your sample, and you put copper as a sample into the vaporization chamber, and the vaporization chamber changes the copper into a gaseous state, into the ionization chamber, attracted and accelerated by the electric plate, And you realize that the number of ions that will be detected on the detector, the recorder will give those number of ions. So you have a correct graph like this. You have a correct graph like this, percentage abundance, the relative atomic masses. Now, when you give the correct graph like this, the number of peaks you see, so you know that copper has 65 copper and 63 copper. So if you use copper in the mass spectrometer, it will give you these two graphs, where one percentage abundance will be around 65 and the other will be around what? The relative atomic masses. So we have the 65 and we have what? The 63. I get it. It will give various percentage abundances. Please do get it. Now, what is the percentage abundance? What is the percentage? So the number of peaks will determine the number of what? Isotopes. So copper has two isotopes, so to provide you with two peaks. Now, the percentage abundance is the proportion of isotopes. Let's write. Percentage abundance is the proportion of isotopes. Is the proportion of isotopes in the total sample. Proportion of isotopes in the total sample, and take to know that the number of peaks would indicate the number of isotopes the element has. Will indicate the number of isotopes the element has. The number of peaks indicates the number of isotopes the element has. The number of isotopes the element has. Now, what is the uses of mass spectrometer? Now, one, we can use the mass spectrometer to determine atomic and molecular masses. We can use the mass spectrometer to determine atomic and molecular masses. Mass spectrometer to determine atomic and molecular masses. Two, we can use the mass spectrometer to determine the number of isotopes. We can use it to determine the number of isotopes of an element. The number of isotopes of an element. Now, what also is the limitation? Limitation of the mass spectrometer. Limitation of the mass spectrometer. Its limitation is that it cannot be used for substances with high boiling point. You cannot use the mass spectrometer for substances. It cannot be used for substances with what? High boiling point. And it can also be used for substances or for measuring the mass of substances that decompose easily. So it cannot be used for substances that decompose. So for substance that decomposes easily. For substance that decomposes easily. Okay. So now I want to take a typical example, a typical Wassce example question, and look at how we can determine the relative atomic masses of the question. Okay. Alright, so this is a typical question, and I want to look at the question. So the question says that the atomic masses of two naturally occurring isotopes of copper with a mass of number of 63 and copper with a mass number of 65 are 62.9298 AMU and 64.9278 AMU, respectively. So that means the 62.92 goes for 63 and 64.9278 goes for 65. It says you calculate the average atomic mass of copper from the mass spectrum below. And then the mass spectrum below. So from this mass spectrum, you realize that the correct drawing on the machine will have been something like this. It will have been something like this. Okay. So now we realize that we have one spectrum which peaks is given a percentage abundance of 70, and the 65 isotope is given a percentage abundance of what? Of 30. And we are asked to calculate the average atomic mass of the copper. The average atomic mass of the copper. So now what happens is that For the 63 copper, it's having an percentage abundance of what? Of 70. And it's having an atomic mass unit of what? 62.9298. Okay. Do you get it? So now, this one, if you are solving a question, make sure you get your parameters down. For the 65 copper, 63. The 65 isotope copper is having a percentage abundance of what? 30, and atomic mass unit of 64.9278. So therefore, to find your average atomic mass, which is AR, your average atomic mass, which is AR, is equal to the various percentage abundances times the atomic mass unit. So the average atomic mass, the formula is the percentage abundance times percentage abundance multiplied by the atomic mass unit, multiplied by atomic mass unit minus all divided by what? 100. So the percentage abundance multiplied by the atomic mass unit. So the difference of that, of the isotope divided by 100 will give you the average atomic mass of the copper. So now what do we get? The 63, so we get what? AR is equal to 70 times 62.9298 minus, so we take the difference of it. I get it. So it's more or less like the difference here. I get it. Minus 30 times 64.9278 all divided by 100. So therefore, the atomic mass of it becomes, if you do these values, you are getting 4405.086 minus 1947.834 divided by 100. So the atomic mass, average atomic mass of the copper then becomes 2457.252. So the average atomic mass, you have to add it. Sorry, you will not find a difference. It's not a difference, it's the addition. So you have to add the two of them. Okay, so let me get my calculator. To add the two of them, so therefore 4405.086 plus 1947.834. Okay, when you do that, you're getting 6,352.92 all divided by 100, and your atomic mass unit now becomes 63.5292. Okay, so this becomes your average atomic mass unit. So take note. It's not the difference in this one. You add it. Are you getting it? Because we want to find the average. So the average is this plus this divided by what? 100. Thank you very much for joining this class.